Get started. Thanks everybody for joining the mini topic today. It's why power cable systems fail. My name is Roy Marshman. I'm responsible for utility and industrial sales for IMCORP. For those who aren't familiar with IMCORP, we provide a 50-60 hertz partial discharge test offline. It's equivalent to what the factory does on components and cables, meeting IEEE or ICA standards. So today we're going to talk about some myths and then kind of break down why cables fail. We've tested about 165,000 segments of cable, equaling about 175 million feet of those cables. So that's we've created a pretty big database, and as far as we know, it's the largest database on cables in the world. So again, talk a little bit about some myths and then talk about the breakdown as we see it based on our information that we've gathered over all these tests. See, I'm trying to advance it and it's not doing it. Oh, here we go. So the first myth is that cables last 30 to 40 years. So we know today in the Houston market, we're testing cables that have been installed before 1979. If you take a look at a cable compared to a medium voltage cable compared to a low voltage cable, a low voltage cable is very simple. It's got a conductor and an insulating top material or jacket. Medium voltage cable, a little bit more complex. Not only do you have a conductor, but you have a strand shield, your insulation, and your semiconductive material. Now, on top of that, you can have a type of metallic shield. In the industrial market, we see the copper tape shield. Typically, in a renewable market or the utility, we have a concentric neutral type shield, and then an overall jacket. So a little bit more complex. But today, we know and we see cables that we're testing in the field that are upwards of 50 years old. And they're operating, if they're installed properly and maintained, protected, are operating better than like new cables. So here we have a cross-section area of a cable that we took to failure. We used legacy tests. We put over voltage on the cable system until it finally went to failure. So we started doing a cross-sectional dissection of the cable right at the fault, and we dyed the cable. We dyed the insulation, and we quickly found that there was a water tree associated with that. Now, we consider a water tree a stress enhancement area, and we do know that water trees are prevalent inside of cable systems all the time. We always see water trees. They're not very hard to find. It's the cable tree, the carbon path, that's the most difficult. Typically, when these go to failure, it's pretty catastrophic and you don't have a whole lot of evidence. But when a water tree is combined with some sort of void, a manufacturer's defect in the cable or an installation area or some contamination, that combination can cause a carbon path or a water tree to develop this path to go to failure. So it goes from your inner conductor, which is the strand shield, to the outer conductor, which is that silicon material. Another myth is that carbon trees will go immediately to failure. Here we have a combination, again, of a water tree and two carbon trees. Now, these carbon trees, we know today and have been able to study them over the last 10 years. They have intermittent growth. They don't just show up and take the cable to failure. As you can see, this particular cross-section hasn't gone to failure. And you see a water tree with it and then the two carbon trees. Interesting to note that the carbon trees will actually go around and over the water tree as opposed to right through the cable tree, the water tree. The water tree is like very lossy for the carbon tree, so it has to actually go around it. So carbon trees do not fail cables immediately. Here we have a cable that has been installed, and this, if anybody can tell, this is a ground rod that's going right through the cable. So I was a helper when I first started working, and I was an electrical helper, and I did a lot of this installing ground rods. And we would install these ground rods and it wouldn't go through. We just move that thing over and find a softer spot. And you can tell where these people tried their first attempt. It didn't go all the way through, so they just moved the ground rod over and went through the cable itself. Now, this cable was in service for a little over 2.5 years. So even though it was a nasty installation, this cable was able to operate in the field for well over 2.5 years. So if we take a look at the water trees and the electrical trees, and then a bad installation, we start forming an opinion that cables take a while to break down. It's an erosion process of the insulation to create a carbon path from the inner conductor to the outer conductor called a failure. Here's a 30-year-old cable that we did a cable life extension program on. This was showing partial discharge. We took a look at this cable and we did a dissection of it. The first time we looked at it, we saw the gash immediately, right? It was showing partial discharge on our testing system. A closer look, there was a cut in the insulation that was well over half the distance of the insulation itself, but it hadn't gone to failure. This is the utility application, so this is 90 degrees C cable, really operates about 40 degrees C. The load is not very heavy on it. So we think because of the size of the gash, or the cut, and the application, this particular cable never went to failure, but we did take it with some over voltage. We were able to find that it was discharging and it had carbon trees that were developing. A closer look at it, you can see some of the water trees that have been developed. We know that it takes decades for water trees to show up, so we know this is an old cable. Here's the QC issue. So this is a termination that's in a downstream application. It's in a refinery. Here you have a conductor, a connector, and you have a cold street termination, and then you have your cable. It doesn't take, if you know what you're looking for, it doesn't take a $1 million piece of equipment to understand that you have a bad installation here. We may cut back some cables to separate the inner conductor and the outer conductor. So we know that a termination, by its nature, has to terminate the electrical stress that are in cables. So this is sitting up a little too high. The electrical stress component that's integrated inside this termination is not sitting over the semicon and insulation interface. So in essence, it's just insulating the cable. We also know that the ground braid rod, it has this black mastic in there. That black mastic is designed to prevent any moisture ingress inside of that termination. Water can obviously get in there because it's not covered properly. So again, it doesn't take a lot of equipment, but this particular termination has been in service for several years without going to failure. So again, and then the erosion process is happening, and it takes time for it to go to failure. Another myth is that the copper tape shield is a robust shield. So I use this for the industrial application that we see today. This is a common design. It's the only copper tape shield overlapping is the industrial market is the only one that uses that today on a fairly common practice. The renewable market and the utility market use a concentric neutral. Now, when this is a new cable, the shield is a good shield. It's very robust. There's really no issue. Typically, when we find problems with cables or termination, it's usually at the termination itself. Somehow, in a contaminated area or environment, moisture ingress can get into the termination. When it gets into or in between the overlapping of the copper tape shield, it can corrode that copper tape shield. By doing that, it interrupts the electrical contact between the overlapping layers. It forces a high-frequency signal to propagate helically versus longitudinally or axially throughout the cable. So it causes a pitting type of action when it sees higher voltages. If this was just at 50, 60 hertz, probably wouldn't be a real big problem. But when it sees these transient voltages, it begins to pit out the semiconductor material. And in this case, a little extreme, it starts to break down the insulation of that cable. Now, when we see issues at terminations, it's an opportunity because today we know that we can mitigate or repair the end of the termination. Here you have a cable that this particular one was 1500 MCM. We worked with the cable accessory manufacturer as well as the cable manufacturer to develop a solution for this. We removed each one of these components, took off the jacket, took off the metallic shield and the semicon, and we were left with some insulation that had been pretty damaged. We were able to buff that out, sand that out nice and smooth, and with an manufacturer's components, had them rebuilt that. We tested this cable at 2 times operating voltage with our testing system, and it held voltage and it met factory standards. Here's another area where the copper tape shield is beginning to erode. It's causing some pitting action. It's completely gone. Once this copper tape shield is completely gone, obviously you can have a floating ground, which can cause its own issues. But this is some of the things that we see in the field with this with copper tape shield. Today, we recommend, and some of our industrial customers are listening to us, and they're using a concentric neutral, which is a little bit robust. Not telling anybody that they should change out, but just kind of giving some facts of some of the issues that we see in the industry when we're called in to do assessments on cables. So we talk about some fundamentals. This is one of my favorite slides. Here you have, it's courtesy of TE. I worked for these guys for 10 years. So I've sold connectors, I've sold cable, and I've sold terminations. So here we have a cutback. It's an exposed naked cutback. There's no sort of stress control mechanism or insulated material on this. So I always ask people, why do you do a cutback when you're installing termination, connecting it to a piece of equipment, or extending a cable with a splice? What happens is you have to create some distance from the inner conductor and the outer conductor. If you had a piece of cable and you just took enough material to put a lug on it and you installed it and energized it, you'd have an immediate flashover. So here you have to cut back, anywhere from 5.5 inches to about 8 inches. Rule of thumb back in the day was for every 1 kV of cable, you had to do a cutback of 1 inch. Today, technology has changed quite a bit, so those cutbacks are a lot easier, are a lot shorter to do. Now, when the electric field is making its way through that cable, all of a sudden it's going to notice that its electrical field has been disrupted. So when it does that, or when it sees that, it turns on itself very sharply. Now, this electrical activity, this glowing, which is known as corona, is a high level of electrical stress. Now, that electrical stress is stronger than the dielectric strength of that insulation. So over time, not in one day, maybe not even in 3 months, this electrical stress will break down that insulation. So that cutback that you made of, let's just say 6 inches, is now creating a clogging path directly to the inner conductor, which will cause a fault. So we'll give an example of what partial discharge is, PD, micro-arcing that does not bridge the insulation between 2 conductors. We see that in most dielectric cables, most of the issues or most of the failures is caused by partial discharge. I'm going to move this over a little bit. I don't know if y'all can see it on my screen, but I see Judd's information. Let me see if I can reduce that. Okay. So I'm having some issues here. I can't start my...
I see your screen now, Roy.
What's that?
I can see your screen. Is that what you're asking?
Yeah. Are you seeing your initials here? I can't get rid of that, and it's not allowing me to go to the next slide.
No, I can't see that. That's probably the participation pop-up, the participant pop-up.
Yeah.
Move it over or close
I
it.
think, okay, I think I'm good here. We talked about this briefly a minute ago. We have an outer conductor on a piece of cable. Now, the concentric neutral here is an example of concentric neutral versus what copper tape shield and what's used in the industrial market. Here, and here we have the inner conductor. We have our insulation, so we're going to install a little void here. So we're going to try to show you what happens from this illustration when you have some partial discharge. So here we have our little air gap, a void in the insulation. And then we have our PDIV and PDEV. PDEV is partial discharge extinguished voltage when partial discharge does not grow. PDIV is a transient voltage. It's a level that's more than operating voltage that ignites the PD activity in the cable. So by looking at this, once we hit partial discharge inception voltage, we begin to see and fire off the partial discharge. Once we go below PDEV, it extinguishes itself. Now, as this begins to grow, this erosion process is happening. That carbon tree begins to grow in the tree. Once it starts Once PDIV gets closer to operating voltage, we know that this excitement of partial discharge is going to be continuous, so it'll eventually break down this cable and cause a fault. So what causes faults in medium voltage cables and high voltage cables? We have electrical trees, which are partial discharge. There's two different categories that we have. We have stress enhancements and we have voids. Foreign objects. So this is a cable that was laid in the ground and then backfilled. A foreign object, a sharp rock, penetrated the jacket, went into the semicon, actually penetrated the insulation as well. We're able to find this. Now, again, with this type of foreign object, this cable could last, 4 or 5 years, maybe even longer, depending on the load, depending on the voltage, but eventually it can fail. Our second application, our second stress enhancement, here is where terminators usually make their money, right here. If they can make a nice ring cut, which is recommended by all manufacturers of components. So when you make that cutback, you have to have a nice, smooth ring cut. You can't have any lips right here. These lips, if you leave that unattended and you don't have any void filler in there, that's a concentration of electrical stress. Again, that electrical stress is stronger than the dielectric strength of the insulation. So eventually, even an EPR will begin to create a carbon tree that will create a path from the inner conductor to the outer conductor, causing failure. Contamination. So when cables are made, it's made in a very clean room. You have the strand shield, your insulation, and your semicon material put over a piece of conductor in a very nice, neat, true triple extrusion, and there's really no contaminants. There's no issue in that area. When you try to do this in the field, in real life situations, you could be inside, on top of a cable tray, inside of a transformer, in a ditch. So these cables can get contaminated. If they get contaminated, that's an area for a void or a stress enhancement partial discharge can be activated. So eventually this cable would go to failure. If you take a look at the ring cut, and I've seen this in the field many times where these guys don't necessarily make a ring cut, they just kind of whittle away the semiconductor material. Again, a lot of sharp points, areas of stress enhancement that can eventually cause this cable termination to go to failure. Water trees. So, of course, we always hear that water trees are going to cause cables to fail. We always say, and we've documented that in combination with a void, the stress enhancement areas will create these and will cause cables to go to failure. But mainly when there's a carbon tree that's associated with it. Now, there has to be some sort of defect, a manufacturer's defect or an installation defect to bring the water to the particular area and then help grow that carbon tree to make that cable go to failure. Here's a manufacturer's defect that we found. This cable was not allowed to cure properly or long enough, so it had a little issue or a void at the strand shield. Now, over time, this would cause a carbon tree to develop, potentially a water tree as well, making a path to the strand shield and the outside diameter of the outer conductor, making this thing go to failure. We were able to catch this prior to energizing the cable. Did it on a commission test. Contamination. So hydrocarbons and carbon black of the semicon do not mix. So this particular one not only had a cut in the semicon, but it was contaminated with oil. Typically we see this at near transformers or where cables may be lying in some sort of hydrocarbon oil type. This will contaminate it. When the hydrocarbon gets to the carbon black, it actually separates the carbon black in that semicon material, causing a more resistance, insulative type material. And then here you see the picture on the left-hand side where it contaminated the cable and made it go to failure. Overheating. So we get a lot of the copper tape spring clamps and the brake clamps. They cause a lot of transient voltages that cause overheating. Connectors cause overheating. when they're not installed properly. The connector is very cable specific, and it has a die that's very connector specific, and it has a tool that's associated with those to put enough and the proper amount of pressure to make a connector. If it's loose, if it has sharp edges, these are areas where it can overheat the conductor or the insulation, causing and breaking down that insulation, causing carbon tracks to eventually make this cable fail. Insulation cuts. This is probably one of the more popular issues that we see out in the field. The guy makes a good ring cut, but his blade goes a little bit too far into the insulation. In this area where we see a lot of electrical activity, that's where we first disrupt the electrical field. That high concentration of activity will begin to break down that insulation in a lot faster fashion. Weren't able to find the issue initially. What we did is we made another ring cut, took this thing back, and we were able to find the cut in the insulation. Really nice thing about if you're using EPR, the guys, we showed them how they can kind of bend the EPR, and there's a discoloration, kind of whitens up a little bit to show any cuts in the insulation. If on something like this, you'd have to do a cutback or make an additional cutback, sand that out to make sure you got the cut out of the system, where an area where you could have partial discharge. So improper installation of void filler. This is another common issue. So some of the instruction sheets that we see will require you, and if you can see there's this red material, that's a void filler by one of the manufacturers that has to set right next to the semicon material. That there's a difference in diameter between the semicon and the insulation. So that step down right there can leave a void, an air pocket in there where energy is ionized real at a high level, like 10 times the voltage, and it begins to break down that insulation. So the components, again, not put on properly. Okay, I'm stuck again. Okay, and then here's our most common issue here. The improper cutback dimensions on terminations as well as splices. Remember, a splice is nothing more than a couple of terminations, but you have to the way the components are designed today, you have to make a perfect cutback so that the stress control mechanism sits right over the semicon and installation of the insulation interface. And it has to put a lot of pressure on that as well. But it has to sit right over this area because what it's doing, we talked about earlier, is it's terminating the electrical stress that's in those cables. If you hit the wrong dimension, you can completely miss the stress control area and put that just on the insulation, and you don't terminate that electrical stress. So obviously that's going to cause an issue because all you're doing is really insulating this cutback. So we talk about, the different ways in stress enhancement and voids because these are all situations that can be avoidable. So if you guys are properly trained in the field and they remove any foreign objects, so there's no, the radial cutbacks are nice and smooth, there's no contaminants, the guys take a lot of careful steps to make sure that nothing is introduced. They clean the semicon or the insulation properly, not the semicon, they don't get the semicon on the insulation. Water trees, eventually water trees are going to form in cable, an H cable, but if it's absence of a void, that water tree won't create a carbon tree. Insulation voids, semiconductor material damage, we know that today if we know what to look for, we can avoid some of these defects that are installed in the cable on installation. A little bit more on the fundamentals of cable. We talk about the stress area, about the semicon insulation interface. It's very high. We talked about how you have a difference in diameter between the semicon and the insulation, and it has that little air pocket right there. There's three ways to eliminate electrical stress in cables. One is with a lot of insulation. We know that that's not practical. We wouldn't get a lot of cable on reels. The elevation changes of the installation wouldn't be very practical. It'd be too heavy, expensive. So today we use a geometric stress control, which is these push-ons type of components, but still used today in some of the newer splices that are out there and some of the load brake or dead front elbows that are installed. It's a lot of conductive material that goes over the semicon with a lot of insulation, and it has this geometric stress control or geometric shape that redistributes that electrical field, so it reduces or eliminates any electrical stress in the termination. Also, impedance, it's a very low profile. That's what we see in most of our heat shrink terminations. Inside of that polymer, that stress control is carbon black. That carbon black creates a unique electrical field, a unique electrical circuit where it's a resistor and a capacitor in series with one another. So these are called pearl chains, and there's a lot of them in there. So you have a voltage drop and a voltage capture, a voltage drop and a voltage capture. And what that does, following the length of the stress control tube, it will eliminate and redistribute that electrical field so that it doesn't damage the cable or the termination. So here, it's an example of a void filler. We got to put a smooth transition in there so that when when the field comes off of the semicon, it's a smooth transition. So there's no big step downs, no air voids, so that air can ionize. So here we're going to show you some growth of a cable. Here, this is a pin type of. I'm going to try to move this again, see if I can get around it. There's a pin that we stuck in some insulation, 100 times the speed. Again, we're going to look at partial discharge inception voltage as well as partial discharge extinguished voltage. Now, once we put this under, let's see, let me start my little video here. So once we put some voltage on there, we're going to quickly see, it's not operating properly. Hold on a second, guys. See if I can reset this. Okay, now we see our voltage meter up the side, up to the right. Once it hits inception voltage, it's going to grow the carbon path to the inner conductor. Once it hits extinguished voltage, it'll stop growing. More transients in the system, it begins to grow. Once we do not get to the level of extinguishing this electrical field, it's going to continue to grow until the carbon path is complete and the cable goes to failure. So that's when we talk about partial discharge inception voltage. Firing off. Okay, almost done here. Here we have an adapter. This is the geometric stress control that I talked about. Could have been an installation issue or just some tracking, maybe on a commission test, some sort of legacy test, but in a lot of voltage on this because of this adapter to track. Here I did an illustration of a, I'm trying to go back here. So this is an actual tree or failure that we had found in the field. And we did this at the University of Connecticut, doing a lot of pictures on CT scan. It took about 4 months to complete. But we found a imperfection, a void in the semicon material. Now that void caused a water tree to locate to this area. So we're going to make this insulation transparent. And we've seen a lot of cross-sectional areas, but here you're able to put a lot of these cross-sectional areas and pictures to get a three-dimensional picture of what this looks like. Here we show where the carbon tree is going over and around the water tree, which is something new. It's never been seen before. We introduced this to ICC last year, but just kind of proves the path of the carbon tree when it's accompanied by a water tree. It's kind of like a gift and a curse because it makes the cable last a little bit longer, but ultimately it will go to failure as long as it's seeing bad and transient voltages. Okay, so today these are our standards. IEEE 48404, 386 are offered the accessories, and then ICEA standards for the medium voltage and high voltage cables. So we test, in the factory test, 50, 60 hertz, what's used in the field today. Now, it's important to know that all cable accessories and cables have some sort of partial discharge in there. Now, is it more manageable? Here we know that, and it's allowed to have 5 picocoulombs of partial discharge in the system at 1.5 times operating voltage, 1.3 times operating voltage on the separable connectors or load break dead front elbows, and then up to 4 times operating voltages on cables. Now, if you have a cable and it passes the IEEE 48, and you put some sort of legacy test on a cable on a new installation, a go, no-go test, DLF test, where you have extended voltage on a cable system at 2 times operating voltage, well, this will create and make this 5 PC area of partial discharge begin to grow. So it's not a test that we recommend on new cables or age cables, because on age cables, if you do have some defects and they have been growing, these types of tests can actually make them grow more. So these are the tests that we adhere to. We do this in the field. This was only these were only tests that could be done in a shielded room at the factory, and these, of course, pass all of these tests before they get to you. It's when we take a component as well as a conductor, and we put those two together. That's when we see contamination in the cable accessories of the cable, as well as cutbacks. We see the workmanship issues that seem to plague us in most industries today. So we know that cables are inherent, because they inherent in the fact that they're exposed to a lot of situations out there, whether it be foreign objects, voids, and these are brought in by the guys that are installing these, and then the operational practices of the application that it's in. So the probability of failure begins to grow when you have all of these issues in the cable. If we eliminate foreign objects or stress enhancement areas, if we eliminate voids, if we're mindful of our operations and our practices of mitigation, we believe that cables today can last for 100 years plus. So that's all I have. At IMCORP, we educate. We have white papers. We probably have more white papers on cable failures than anybody. These are available for anybody who wants them. We do education as far as show the guys what to look for in the field. We have seminars that they can subscribe to. If you have an H cable system, we're able to go out there and find the cables that are bad. So you don't replace all your cables, you just replace the ones that are bad. Because we know based on our database that 60% of the cables that are installed today are working and would meet factory standards that they were designed to. The other 40% either need some sort of repair or mitigation, and then about 20% of those half of those have to be replaced completely, just because they may have had some additional splices put in there and used some legacy tests that can actually break down some of those cables, or any partial discharge can expose them, or if you have the ground that has been deteriorated and the cable just needs to be replaced. So I hope you learned a little bit about why cables fail. If anybody wants more information, please let me know. Be more than happy to give you the white papers, case studies, or just our experience on any issue that you may have.
Well, great presentation, Roy. There's a couple questions. Let me take presentation from you, and I'll show you questions.
Okay. Okay, I thought I was running out of time there.
No, you're good. That was a great presentation.
Okay, good.
So you should see there's a couple questions on your screen from the audience.
Yeah, so first question, can you expand on the differences between a water tree and a carbon tree? Okay, so very different. We know that a water tree is it's a very lossy type of application. So a water tree is where there's been some sort of water ingress into the cable, because we all know that there's going to be water in cables, and this water tree will begin to grow. It takes decades for a water tree to grow. And what it is just an area where there's no electrical activity. Again, very lossy type of cable, and we find these all the time within a cable system. Now, a carbon tree, that is creating the direct path between the inner conductor and the outer conductor. So that's your main conductor, and that's your semicon material or your shield that is creating that path. When you hit an inception voltage, it begins to grow that carbon tree. And that carbon tree minus a water tree would typically go very vertically and directly to the outer conductor, or vice versa. It can go from the outer into the inner conductor. So the difference is one will fell a cable ultimately. The carbon tree will fell a cable, the water tree won't. The carbon tree is nothing more than a path, a hole in that cable connecting those two conductors, inner, outer. And remember, that's why you make a cutback. You got to separate those conductors, because if you don't, they'll flash over. When you break down that cable, that's when you'll see the path. All right, you mentioned using proper ring cuts. Is there a qualification test agency that an installer can obtain to show that they are competent? There really isn't, not that I know of. It really just takes years of experience and knowing what to look for. So today, when we started getting into the renewal business, a 35 kV cable is not very forgiving. So those cables weren't lasting very long. 100% load, 90 to 100% load, 35 kV class. So an imperfection in that ring cuts was going to show itself pretty quick. It could last a week, it could last 6 months, but it would ultimately fail. When we went out there and we showed the guys, and it's kind of like over and over, we would test the cable, there's partial discharge there, and we would look at that cable with them together, and we would show them where it wasn't a proper ring cut, or where there might have been some contamination, or where there was the ring cut was too deep, or it had like a little point on it. It's just experience. So I've been to many places where people have gone, "Hey, Roy, come show us how to install one of these cables." One thing I did is always did the theory portion of it, and then I showed them why they had to put a termination on a cable. And when you take a look at that ring cut, I would look at some of the guys and they said, "These are my best guys, and don't worry, because I'm going to be watching them." I would make them do cutbacks, and I would observe those cutbacks, and they'd always have some points on them. And to them, they're saying, "Well, I can get away with that. There's not a problem." Because, again, these cables will last for a very long time. It's an erosion process that can take a very long time to happen. But I don't know of any tests that they can take. I said at a later time, could IMCORP illustrate the difference cable testing methods and the methods IMCORP recommends for different types of cables? We'd like to do that. We have great white papers on VLF, and delta, AC withstand, low frequency. So we have all of those papers, but we would be more than happy to present to you guys and show you the difference. Now, our test is not considered destructive. We're on a cable for about 40 to 60 seconds. We go from operating voltage, we'll go to 1.3, 1.5, 1.7, 2 times operating, up to 2.5 times operating voltage. Typically, we don't go any higher than that because we are going to recommend surge protection. So the margin of protection on that cable system should never see over 2 times operating voltage. But any voltage on a cable can be devastating. It can be destructive. We just stay on it for a lot less time. In that 60-second time frame, we can capture all the information, a foot-by-foot profile of that cable, and tell you if it's good, if it's bad. We can even show you that a prioritization list or the risk of failure for these particular cables. I hope that answered those questions.
No, I did. Great job, Roy.
Let me go back to the ring cut. Just for the ring cut, you can't get these guys to use knives. I mean, because they can make a great ring cut on Monday, and Friday when they're ready to get out of there, they don't make a good ring cut. If it's in an elevated area, they don't have their feet below them, they don't have a good grasp of that cable. It's moving around quite a bit. They got one hand to hold the cable, one hand to make the cut. There's great tools out there by Speed Systems, and I'm forgetting a couple of the other names that give you a more consistent cut time after time. That I would recommend using some sort of tooling equipment versus any knives out in the field.
That's good, man. We can put a link on the forum for those tools.
Okay.
All right, Roy.
Well,
Thanks again.
You bet. You bet.
We're gonna finish up here. Let's see. Upcoming meetings. We got next week, June 5th. Dr. Tony Parsons from Snyder is going to do a presentation on passive arc fault mitigation. And on June 26th, Greg Kev with Siemens is going to be presenting differences in available UPS technologies available to us. So thanks, guys. Thanks, Roy, and we'll see y'all next time.